In this video, we'll be graphing quadratic functions that are written in standard form and then identifying their key components. So here you can see standard form, and a couple of things I want to hit on with standard form is that this is the form where we have all of the parentheses gone and everything's multiplied out with like terms combined. And this will be written in the form y equals ax squared plus bx plus c, where a is this coefficient of x squared. Then we have the b value here, which is the coefficient of x, and c is our constant value on the end without any sort of variable value attached to it. So then from here, what's difficult about standard form is unlike vertex form where we can see how the graph moves using h and k. So in vertex form, we were able to use h and k to find our vertex. It's not so simple with standard form. And we actually have an equation here that's going to help us calculate our axis of symmetry. So our equation for the axis of symmetry for standard form. And that equation is going to be x is equal to negative b. So we would take this b value here, and that's our opposite of b. That's what that negative really means. So opposite b divided by 2 times a. And we'll use that equation whenever we have standard forms. Notice a and b come right out of the equation. And we'll use that in order to calculate our axis of symmetry algebraically. So before we start to graph these, we're going to actually identify the axis of symmetry for each of these functions that are written in standard form. And remember, we're going to use the equation x equals negative b over 2 times a, or x equals opposite b over 2a. So what we're going to start off doing is for each one, we're going to identify a, b, and c. So a is our coefficient of x squared, so this is a is equal to 3. B is our coefficient of that middle term with an x, so we have b is equal to negative 12, and c is equal to this constant on the end of 5. So our equation only needs the values for b and a. So here we have the equation x is equal to negative b, or opposite b, so we take negative 12 and we turn it to its opposite, which is 12, over 2 times a, which is 3. So then we need to simplify this to find our axis of symmetry. So we end up with 12 over 6, which is then equal to 2. So our axis of symmetry for the equation in part A is x is equal to 2. Then if we move on to example B, we have our a value, which is the coefficient of x squared, which is a negative 1. Our b value, which is the coefficient of x here, which is 10. And our c value, which is the constant at the end, which is non-existent, or just 0. So we only need our b and a values in order to calculate our axis of symmetry. So we have x equals negative b, or opposite of b, so it's a negative 10, over 2 times a, which is negative 1. So here we have negative 10 over negative 2. Negative over a negative gives me a positive. So my axis of symmetry here would be x is equal to 5. Then if we move down to example C, we have a is equal to, we have negative 8. B is equal to the coefficient of x, which is 4. And c is equal to this constant here, which is negative 5. So to calculate our axis of symmetry, we have x is equal to opposite b, which is negative 4, over 2 times a, which is negative 8. So here we have negative 4 over 2 times negative 8 is negative 16. Negative over a negative is a positive, and this fraction simplifies to 1/4. So our axis of symmetry here is x is equal to 1/4. So you can see here that there are times where our axis of symmetry is not a nice number and a fraction. It doesn't happen very often, but it is in fact possible. And then our last example here, we have an a value equal to 1, because that's the coefficient of x squared. This one, I'm going to pause and slow down for a second, can be pretty tricky because we actually don't have a b value in here. So normally we have plus b times x, but because there's no x value here, we actually have a b value equal to 0, and then a c value equal to negative 16. So just make sure you slow down as you encounter these ones mixing that x term in the middle, they have a b value of 0. So then here our axis of symmetry is x equals opposite b, which is opposite of 0, over 2 times 1, which is our a value. So this becomes 0 over 2, which is equal to 0. So our axis of symmetry here is just x is equal to 0. So let's jump on in and start this example here. So here we see we have something written in standard form. So just like with vertex form, we're going to start by finding our vertex and axis of symmetry, but here we're going to have to do something a little bit more complex because we don't have that information right in our equation. So we're going to start in standard form by finding our axis of symmetry. And remember, we find our axis of symmetry by taking x equals negative b divided by 2 times a. So we're going to start by identifying our b value, which is this positive 6 here. So opposite b, or negative b, becomes negative 6 over 2 times our a value here, which is negative 1. So 2 times negative 1. So here we have negative 6 over negative 2, which when we divide becomes a positive 3. So what we found to start off is that our axis of symmetry is x equals 3. So the middle of our parabola, or the middle of our quadratic function, is going to be right here on that dotted line. Then after this, we actually need to calculate our vertex. And remember, there's a really cool relationship between our axis of symmetry and our vertex. They share an x value. So you might want to make a note of that. They share x. So since we know our axis of symmetry, we know the x-coordinate of our vertex, which is 3. So what we need to do here is we need to utilize this equation up here and calculate the y value that goes along with that x value of 3. So we're just going to do that algebraically. So here we have y is equal to negative 1 times, we have 3 squared, plus 6 times 3 minus 8. So just using my order of operations, I'm going to start right here. So I have, well, 3 squared is 9. Times negative 1 is negative 9, plus that becomes 18, and then I'm going to use keep change here and do plus a negative 8. So negative 9 plus 18 is 9, 9 plus negative 8 is 1. So here I have a vertex point of x is 3 and y is 1. So we can go right here, and there's our vertex point of x is 3 and y is 1. Then from here, we need to identify some more key points. So what I'm going to do is I'm going to put my vertex here in the middle, and I'm going to calculate some points around it. And you can calculate whichever points around it that you would like. I'm going to start by calculating when x is 1 and x is 2, and then using my knowledge of symmetry to find those other points for x is 4 and x is 5. So I start off with x is equal to 1, and we're going to use our equation here. So we have y is equal to negative 1 times 1 squared plus 6 times 1 minus 8. Well, I know from here that 1 squared is 1, and 1 times negative 1 is negative 1. So I have negative 1 plus 6 plus a negative 8. Well, negative 1 plus 6 is 5, and 5 plus a negative 8 is negative 3. So here I have the point x is 1, y is negative 3. Then I know that this, because of symmetry, 5 is also going to be negative 3. So I can apply that right away and see the symmetry around it. Then I'm also going to find x is equal to 2. So I have y is equal to negative 1 times 2 squared plus 6 times 2 minus 8. So I go ahead and I say, well, I have 2 squared, which is 4. 4 times negative 1 is negative 4, plus that's 12, and then I have plus a negative 8. Well, negative 4 plus 12 is 8, and 8 plus negative 8 is 0. So these two, our points are 0. So we have 2, 0, and 4, 0. So here I can see a general sketch of my quadratic function. So now what I need to do is I need to identify the remaining key components here. So if I take a look, there are some that I can calculate pretty easily. My domain, I can see my graph is going forever to the left and to the right, so I know that my domain is all real numbers. I also can see that the highest point on my quadratic function is y is equal to 1. So my range is y is less than or equal to 1. I then also can see where my graph is increasing and decreasing. It's increasing here to the left of 3. So you remember you can write left of x equals 3, or you can just write when x is less than 3. Either way is fine. Decreasing is here on the right, and here I have where it's right of x equals 3, or you can write x is greater than 3. We also can see here that our vertex point up here is the highest point on our graph, which makes our vertex point a maximum point. So that's pretty nifty. Then from here we can see our x-intercepts point where we're crossing the x-intercept, and that occurs when x is at 2, 0 and 4, 0. And the last thing here that we do need to calculate, but it's a pretty easy calculation, is our y-intercept. And remember, our y-intercept occurs when we cross the y-axis here, and it occurs when x is equal to 0. So all we need to do here is take our function and set x equal to 0. And luckily in standard form, this is pretty simple because we have 0 squared and 6 times 0 here, because those terms all become 0, and we're left with a negative 8. So our y-intercept occurs when x is 0, y is negative 8, which we can see is pretty close in our sketch here. So here we have our first equation that we've graphed in standard form using our standard form axis of symmetry equation, and then identifying all of the key components once we have that graph complete.